Okay, in this segment we're going to look at another example of using superposition to analyze a circuit. And this is, again, a sort of divide and conquer approach. The network we're going to be looking at here is as follows. So we've got the 2R, this one goes to ground. We have an R, a 2R, an R, a 2R, and another 2R here to ground. And we have 3 input voltage sources here. And we're going to call this one VN0, VN1, well, let's call this V0. We'll just call this V0, V1, and V2. And our output is going to be right here. And we'd like to know, how does Vout, the voltage across this 2R resistor here, depend on these 3 voltages here, V0, V1, and V2. Now this is an R-2R ladder network, similar to the one that you'll be looking at in Lab 1, but it's used in a different way. And so this is, has several input voltage sources, and so this is a good candidate for superposition. So what we're going to do is we're going to say that Vout is equal to Vout 0 plus Vout 1 plus Vout 2, where Vout 0 is the component of Vout due to V0. Vout 1 is the component of Vout due to V1, and V3, or rather Vout 2, is the component of Vout due to V2. And so let's start with the voltage source that's closest to the output here. We'll start by looking at Vout 2. And to get Vout 2, what we're going to do is basically disable or turn off V0 and V1. And you remember the way that we do that is we basically replace them with a short circuit. Like so. And we're interested in what is Vout 2, which we could label here on the schematic Vout 2. So that is the component of Vout that we're looking at. Well, here we have to the left of this point, we basically have a simple ladder network that we can easily collapse into a single equivalent resistance. We could write down what that is: R in series with 2R parallel R in series with 2R parallel 2R. Or we can take a look at this and recognize here we have 2R in parallel with 2R, and we know that two resistors that are equal to each other in parallel just become half of either one of them. So this whole thing collapses into an R. R in series with R becomes 2R. 2R then would be in parallel with 2R, so 2R in parallel with 2R is R again. And then we have R in series with R, and so we have a 2R. So, sorry about that. To the right here of this point, it's equivalent to a single resistor 2R connected to ground. And so what we have here is we have V2 coupling through a 2R resistor into a node here where we have 2R hanging off that way and 2R hanging off that way, and those are in parallel. So we have 2R parallel 2R, and that becomes R. And so V out 2, and the circuit really looks something like this. We have V2, 2R, and so, like I said, these are equivalent to a single resistor whose value is R. And so this is just a simple two-way voltage divider. And so we have V2 times, well, it's R over 2R plus R. Or V2 times 1/3, because the R's cancel. R over 3R. Okay, well, that was reasonably painless. Now we're going to go on to say V1. So we put V1 back. And we replace V2 with a short, like so. And we're interested in V out 1. Well, we can do a similar thing here. Here V1 couples in into this node up here through 2R. And to the left of this point, and to the right of this point, we actually have two identical networks. Right, so let's call this point here VA. And we could collapse this ladder into a single equivalent resistor pretty easily. And we can collapse this ladder into a single equivalent resistor, which is exactly the same as this one. And so those two would appear in parallel, and we could get VA as a simple voltage divider from V1. Right, so 2R parallel 2R is just R. Right, so these two resistors collapse into a single R. R in series with R gives us 2R, and so from here over, this is effectively just a 2R to ground. Likewise, from here over, this would be a 2R also to ground. And so 2R parallel 2R is just R. So to start out with V out, we're going to write down V1 coupling through a 2R into an R. And so to get VA, there's a voltage divider, which would be R over 2R plus R. So this is VA over V1. And that gets us the voltage on this node here. And once we have that, then we can think about expanding in our minds this part of the network out, or focusing on this part of the network over on the right. And we have effectively a succession of two voltage dividers, because once we have VA, then Vout1 is just a simple two-way voltage divider from VA. Right, because we have 2R in parallel with 2R, that gives us an R. So these two resistors here collapse into a single equivalent resistance of R. And R in series with R is just a simple two-way voltage divider with a divider ratio of 1/2. And so to get from VA, which is the product of V1 times this divider ratio, we simply write R over R plus R to get from VA to Vout1. And so this is just V1 times 1/3 times 1/2. Again, the R's cancel, and it all goes away. Okay, so that was V1, and now we're going to erase V1 and replace it with a short, and we're going to reinstantiate V0. And here, we have a situation where we have a 2R resistor over here to the left, and then this whole network over here to the right can also be collapsed into a single equivalent resistance. And we can do that conveniently by starting over here to the right. 2R in parallel with 2R gives us an R. R in series with R gives us a 2R. 2R in parallel with 2R gives us an R, and we have an R in series with R gives us 2R. And so we have here again a situation where we have V0 coupling in through a resistor of 2R into this point, so we could call this maybe VB, coupling into VB. And VB is a simple two-way voltage divider from VO, like this. So we have a situation that's like VO, coupling in through 2R into a 2R off to the left, and a 2R off to the right. And this is basically VB. And so again, 2R in parallel with 2R is just R, and we have a divider of R divided by 2R plus R, which is again a 1/3 divider. So Vout 0 is V0 times R over 2R plus R. And this is VB over V1. And once we have VB, we can get VA by collapsing all of this into a single equivalent resistor, and we have a simple two-way divider again. So this equivalent resistance, we said before, was just R, right? So reminding us ourselves of that, we have 2R parallel to R gives us R. R in series with R gives us 2R. 2R parallel to R gives us R. So this is just basically R in series with R, and VA is the middle of that two series resistor chain. The divider ratio is 1/2, R over R plus R. So this is VA over VB. And then once we have VA, we again can get Vout, in this case it's Vout 0, as again a simple two-way voltage divider, where we lump the 2R in parallel with 2R as a single R. We have R in series with R, and we have our two-way voltage divider ratio with a ratio of 1/2, R over R plus R. And this is V out 0 over VA. So it's again a succession of voltage dividers. Here there's actually 3 two-way voltage dividers that stack up here, making our overall component of Vout equal to V0 times 1/3 times 1/2 times 1/2. So we can combine all of these things and write that Vout is equal to V2 over 3 plus V1 over 6 plus V0 over 12. Now, so let's put all these back here. And this was V1 and V2. So we didn't say anything about what these V0, V1, and V2 are. We didn't make any assumptions about what values they had. Let's assume that input V sub I is of the form some Vref, some reference voltage, times a variable which we're going to call B sub I, where B sub I is an element of the set 0 and 1. So BI is a bit. A binary digit can be either 0 or 1, which means that depending on the value of BI, these voltage sources are either 0 or they are Vref. And with that in mind, we can substitute that into our Vout expression and write that Vout is equal to Vref over 3 times B2 plus Vref over 6 times B1 plus Vref over 12 times B0. Let's factor the common let's factor a common thing out of this. Let's factor out a Vref over 12 to make the coefficient of B0 1. So that gives us a Vref over 12 out front. And in order to get Vref over 3, when we multiply by Vref over 12, we're going to need to leave a 4 behind. So 4B2. In order to get a Vref over 6, when we multiply by Vref over 12, we're going to need to leave behind a 2. And then, of course, a 1B0. Well, that's interesting. These binary numbers are weighted by successive powers of 2. So this is 2 to the 0, 2 to the 1, and 2 squared. So this is Vref over 12 times 2 squared B2 plus 2 to the first times B1 plus 2 to the 0 times B0. Now, This may strike you, if you know anything about the binary number system, as interesting, because what this is a weighted sum of some bits where the weights on the different bit values, or binary digits, is the positional significance in the binary number system. So B0 would be the least significant bit of a 3-bit number. B1 would be the 2's digit. So this is the 1's digit, the 2's digit, and the 4's digit of a 3-bit binary number. And with this sort of interpretation of the inputs, so this was B0 vref, B1 vref, and B2 vref. This network, the simple resistive network, is a 3-bit digital to analog converter. Produces an output voltage that is proportional to the binary number that's encoded by these 3 bits. And this R-2R ladder network is giving us the proper weighting of the input voltages, which are either low or high, and it's also providing, via superposition, the summation. So this is actually a really, really cool resistive network. This is one of my favorite, this R-2R ladder network, in several of its different uses. I think is probably my favorite resistive circuit. Now, resistors are kind of boring devices. We use them a lot for certain things, but they're usually pretty dull and pedestrian things. This use of a resistive network is actually really super cool. This is about as good as it gets with resistors. This format of a DAC is actually very well suited to a situation where you have something like a microcontroller and you've got a bank of digital output pins that you can set either low or high at ground or VDD, and you can often control all of those bits by writing a single binary number into a register, and those values are all asserted simultaneously. And so if you build this kind of resistive network and just put the digital outputs of the microcontroller on these points in the circuit, assuming you've picked your R so that it's capable of being driven by the microcontroller I/O pins, you've got yourself a pretty reasonable digital to analog converter, which is kind of nice because not many microcontrollers come with an actual digital analog converter that produces an output voltage. So this is extensible to as probably realistically as many as 8 or 10 outputs before the mismatch in the resistors really prevents you from making a nice linear transfer curve for your D to A converter. You need about matching within 1 part and 2 to the n to really make a good monotonic linear digital analog converter. And 0.1% is 2 to the 10th, or 1 over 2 to the 10th. So much above 10 bits, unless you've got some really super well matched resistors, is probably pie in the sky with this approach. But what you would do to extend this is you basically just put another R, 2R, R, 2R, R, 2R with more voltage sources here, and you have to preserve what this N structure looks like. So on the last voltage source you would hang another 2R off in parallel to ground, and that would become your Vout. So just to make that explicit, if I wanted to extend this to, let's say, 4, How would I do that? Well, I would erase that and replace that terminal structure with an R. We have a 2R. Our new most significant bit be 3 vref. And then we would hang another 2R off here in parallel. And this would be V out. So the unit cell, if you like, is sort of the structure. And we have a terminal structure here on the left and a terminal structure on the right. So that's going to be our second example of using superposition to do a circuit analysis. You could also analyze this network with nodal analysis, and it wouldn't be too bad for our 3-bit D to A converter. You would have basically 3 nodes, so it would be a 3x3 matrix. Yeah, solving the 3x3 matrix system of equations without throwing it into some sort of symbolic math package is going to be a little painful. The matrix is very regular, but it's still a little painful. So I hope you'll agree that the superposition analysis wasn't too bad once we recognize this sort of alternation between R and 2R and the equivalent resistance as we kind of alternate going through successive nodes in the circuit. And that made writing down the voltage divider ratios very easy. So anyway, that's it for this segment, and we'll see you next time.